Based on an orbital radius of 239,000 miles and the synodic period of 27.3 days, what is the acceleration of the moon? How many times larger is the free fall acceleration on Earth of maybe, say, an apple? So we're kind of doing the same comparison in this example as we did in the previous example, but now maybe from a slightly more modern point of view, we're going to compare the acceleration of the one object to the acceleration of the other object rather than comparing how far each one fell in a second. As part of that, we need to figure out the acceleration of the moon based on the two numbers that are given to us, and those kind of, you could say, represent the observed acceleration of the moon. And if we model the moon as having a circular orbit, then I think the formula I'd like to start for considering that is the centripetal acceleration formula for circular motion. So again, modeling it as a perfectly circular orbit. In reality, it's probably not a perfect circle, but we're going to assume this model is close enough. Now, I'm not exactly given those values. Well, maybe I'm given one of them, right? Because if I look at the 239,000 miles, I think that being an orbital radius, that's what r is equal to. So I can assign the variable of r to that, or maybe assign that number to the variable r is what I should say. So there it is, 239,000, again, miles. And maybe the simple thing I could do with this is multiply by the fact that there are 1,609 meters in 1 mile. And then let me quickly consult my calculator on this one. Because let me see, this gives me the value of, let me see, here's what the calculator spits out. I need to, oops, make that a better 8384551,000. So let's see, that's like what, 384,551,000, right? Meters. Okay. We're also given the synodic period, which is not the orbital speed v. So v, I think, would, like if I said, hey, do I have a number to plug in for that? I need to be given the orbital speed of the moon, which I was not given. I think it might be appropriate for me to assign that 27.3 days to the variable t that is customarily used to represent the period of something. And again, so that's 27.3 days, but recognizing that there's 24 hours in a day and that there is 3,600 seconds in an hour, I can go through these conversion calculations. In other words, enter 27.3 times 24 times 3,600, and the calculator gives me the following number that I'll try to copy correctly here. Okay, so what is that? That's like 2,358,720 seconds. Okay, we got some pretty big numbers there. But how can I use? So I've got these two big numbers for t and r, and I think the thing to recognize, maybe the thing that will help me out, is to recognize, as we did earlier at some point, I remember doing this, is that the orbital speed should be distance over time, and if the distance is the orbital circumference in the form of 2 pi r, and t represents the period along, that it takes for the orbit to complete that distance, then this really should be that speed. And so based on that, the centripetal acceleration will be equal to, let's see, 2 pi r over t, all squared, and then still divided by another r, which at the end of the day I could write that maybe as, I'll just say 2 pi squared times an r over a t squared. So in my calculator, I could have also, I guess, distributed this to make this a 4 pi squared, or you could put it in that way in the calculator, whatever you like. And we have to put in these gigantic numbers. So the 384,551,000 meters. And then don't forget, this one's got to be squared. So that was the, I think it's 358,720 seconds. But that one's going to get squared. And I've kept my units here, and notice that that is an acceleration. So I can go ahead and calculate this now. And my calculator gives a number of about 0.00273, rounding up slightly there. It's like 287, but 273 meters per second squared. The second part of this calculation or question is how many times larger is the free fall acceleration on Earth? In other words, how much bigger does 9.81 represent compared to this, right? So if I just take 9.81 and divide by that number, and I'm going to do that now, and I get about 3,595, although recognizing that maybe we were given numbers at a 3 significant figure level, this could be just rounded, I think, to 3,600, which exactly matches what we predicted in the previous example. I wouldn't necessarily have expected it to be a totally exact match. It's kind of, everything has uncertainty in it, so you can never really reasonably expect that. But again, this kind of confirms the same thing. In that sense, one could say that the prediction using Newton's law of gravity is that 3,600 ratio between these two accelerations, and everything else we did is based on observations. 9.81 comes from observations of free fall here on Earth, and this really exceedingly small acceleration of the moon came from calculations based on its known orbital properties.